I think it's so important to be well-read, to understand history. Science is a part of history. To understand science's role in our community, in the world, you need to understand all these other things.
The point that Moungi Bawendi is bringing up there is something that always fascinates me when I'm talking to Nobel laureates. This idea that you have to be so focused on a question that you can go further with that question than anyone has been able to go before, and yet keep an eye on the broader picture. Have the latitude to be both super focused and, in Moungi Bawendi's case for sure, super broad. And certainly that breadth then informs what you focus on and how you focus on it. Bawendi in particular has so many outside interests: sports, ice climbing, playing the violin, reading Zola. Nobel laureates are all different. And do join me as we explore what it is that motivates and interests Moungi Bawendi.
This is Nobel Prize Conversations. Our guest is Moungi Bawendi, the 2023 laureate in chemistry. He was awarded for the discovery and synthesis of quantum dots and shares the prize with Alexei Yakimov and Louis Brus. Your host is Adam Smith, Chief Scientific Officer at Nobel Prize Outreach. This podcast was produced in cooperation with Fundación Ramón Arefes. Moungi Bawendi is the Lester Wolfe Professor at the Massachusetts Institute of Technology. He talks to Adam about how, as a 10-year-old, he ploughed through the complete works of 19th century French author Émile Zola, why what you don't understand should excite you, and how for him, rock climbing puts the balance in work-life balance. But first, techniques may advance at breakneck speed, but the scientific process remains the same.
I wanted to start by reflecting on the extraordinary pace of change in science. I mean, you're a relatively young chemistry laureate, but even in your career, there's just been a staggering change in the field. When you were an undergraduate studying chemistry and physics, quantum confinement, the idea that you could change the properties of tiny particles depending on their size, was something you read about in textbooks. It was theory. And now we're surrounded by devices making use of technologies that have been developed by you and others that use the principle of quantum confinement. It's just a wonder how fast things change, really.
I couldn't agree with you more. The pace has been incredible. I mean, when I look back on just the equipment that we were using when I was an undergraduate, I mean, we didn't have computers set up to run experiments back then. Everything was manual, knobs and stuff like this, and pens. We didn't have screens to look at. Everything was analog pretty much. And the acquisition of data is so much faster today. I mean, part of the change is really the ability to cycle through data so much faster than we used to. That's for the acquisition. And then the analysis, so much more powerful today. My students can sit at home, run the experiment from home, and then on their PC, just run incredibly sophisticated software that you just couldn't do. In 15 minutes, they can do something that would take months when I was starting out as an undergraduate on a big computer that you had to have special access to. It's just amazing. So, quantum confinement is certainly one thing, but I see, in nanoscience, there's so many other materials that have popped up since then, all the carbon-based materials like graphene and things like this, and nanotubes and buckyballs that are part of the, the everyday world also. And then in biology, biology has seen incredible progress, and it's just a completely different world. And it just keeps accelerating, it seems.
I imagine that as a scientist, you don't feel very different from how you felt when you first embarked.
Yeah, and so in terms of the thinking, in terms of the questions that we ask, it's the same process. You get excited by results that you don't understand. The unexpected is what we, as basic scientists, what we live for, trying to understand it and make sense of it and move on. But that cycle time is much faster. We're able to ask much more sophisticated questions now than we were able to do before because of the availability of equipment that wasn't there before. I would say the one thing that hasn't changed in terms of slowing things down is our ability to make samples. Once we have samples, we can really run them through a gauntlet of really sophisticated tests. But
that was the key thing that you worked on for so long, wanting to ask questions about the physics of quantum dots, but needing to be able to make things that were reproducible that you could actually study.
Yeah, that part is still really painfully slow.
It's so early in this conversation, Adam, and I already have so many questions. You've mentioned quantum dots. Moungi Bawendi's mentioned quantum confinement. Can you help us to understand what's going on here?
Yeah, it's getting complicated quickly, isn't it? Oh dear. Quantum dots are tiny particles that behave differently depending on their size. And in Moungi Bawendi's hands, they become particles which have a whole spectrum of different colours, which have become incredibly important in all sorts of different applications. They're an example of quantum confinement, which is really quantum mechanics in action. When a particle becomes very small, the electrons in it can not go anywhere. They're confined within a particular space. It's often described as the particle in a box situation. Mm-hmm. And that constrains the energy levels that the particle can have. And the transition of electrons between those energy levels creates different sorts of properties, including that they shine in different colours.
I love this idea of them shining in different colours. What sort of size does it have to go down to for that to happen?
Very good question. We're talking very few nanometers, sort of the 1 to 10 nanometer range.
Amazing. That's hard to sort of visualise, but
10 to the minus 9 meters. Yes, it is hard to visualise. We're above the atomic scale, but we're just a few molecules put together, a few atoms put together.
So I guess at that kind of scale, it must be very hard to make and work with samples like this.
Incredibly. And one of Moungi Bawendi's great contributions was to take the initial finding that his supervisor at Bell Labs, Louis Brus, who shared the prize with him, had made, which was that properties were changing with the changing size of these semiconductor particles, and get to the point of being able to reproducibly make particles of a certain size, which would then have dependable properties. That was a huge breakthrough, being able to make that happen.
And what are the applications of that? Once you can make those dependable size tiny particles, what can be done with them?
Well, then you can have things that have a particular colour and dependably have that colour, and then they've been put in, for instance, the quantum dot screens on our flat screen TVs.
Amazing.
They can be used for biomedical applications. They can also be used for all sorts of electronics applications. The world is just beginning to find out what we can do with quantum dots.
Were the applications evident early on?
I don't think they were at all. I can't say whether they had an inkling that things might come out of it as they did, but the initial discovery was made for completely different reasons. They were studying semiconductors. They made an observation that quantum mechanics was becoming real in front of their eyes, if you like. They got interested in that and they studied that because it was a fascinating question. What's going on here? Certainly at that point, there was no thought of, okay, and what can we make out of this? It was just pure fundamental curiosity that was driving them. And in our conversation, Moungi Bawendi himself makes that point very strongly.
If you look at technologies that we have today, they have roots 20, 30, 40 years ago in curiosity-based research, questions that people were asking because they saw something that they didn't expect or because they were exploring a topic with no real idea of where to go. You know, it's not something you can write in a grant proposal. I'm going to do this, this, and this, and in 3 years I'm going to get this, you know. That's not how curiosity-based research works. You start off with an idea, and then you've got to switch. There's always these bifurcations, and you change path depending on what you see. And you have no idea really where it's going to go, and you certainly don't know what the applications are going to be. When we first started this quantum dot business, when I was at Bell Labs and when Louis Brus and his co-workers were studying, the application initially that was in mind was to use these things as lasers. I remember, you know, when we made the little solutions of these quantum dots initially, the first thing we did was to put them in front of a high-power short pulse pump laser to excite them in a cavity and trying to get these things to laze, and they just would not laze. One of my colleagues at the time said, you know, you can get blood to laze here. These just don't laze. So, clearly, that was the wrong application.
Indeed, indeed.
The motivation was basic science. The motivation was to understand this transition from atomic properties to bulk properties. They're so different from one another. An atom looks nothing like the bulk, and the bulk looks nothing like the atom that it's made from. So somewhere along the way, you have to have a transition from the atomic to the bulk properties. And how does that transition go about? How big do you have to be? Are there any special things that happen in between? That's really the overarching curiosity question that drove this.
It's such a beautiful question. How do you go from the atom to the bulk solid? What happens?
Right. And it's a question that was being asked at the time by a bunch of different communities. So the closest community to us was largely physicists, but also some chemists studying clusters of metal atoms made in high vacuum in something called a molecular beam. Basically, you have a furnace and you heat up a vapor of a metal, and then you have these atoms that are now in the gas phase, and then in a normal pressure sort of chamber, and then you have a little hole, and then you have a stream of these atoms that now go into a high vacuum chamber. And as they go in that stream, they collide with each other and they begin to form clusters of 5, 6, 7, 8 atoms. And then you send these through a mass spectrometer to analyze how many atoms you have. And then the first thing you do is you ask the question, are there any special clusters that come out, ones that are more stable than others, magic sizes? And so you find that, yes, indeed, there's some numbers of atoms that are favored, that seem to be more easily made than others. And then you go to the theorist and they calculate the structures of these 6, 7, 8 atom clusters and try to understand how they're bonded together. And it's sort of like the reductionist view. I start one atom at a time and I begin to build the bulk. If you do it one atom at a time, it's going to be a really slow process to get to 1 million atoms. But those are very clean experiments. They're beautiful experiments. Since I started in this field 30 years ago, basically, our interest was really focused on the small particles, the ones where quantum confinement was really obvious. You see these transition of colors, from the quantum dots. That's really obvious. Your eyes sees the quantum mechanics. It's an incredible visual gratification.
That's an amazing statement. Your eyes see the quantum mechanics. Would you have imagined as an undergraduate that you would be in that position of making that change happen before you on the bench?
No. I mean, you could say that your eyes see quantum mechanics all the time because quantum mechanics is at the root of everything that we see. Making up molecules from atoms, that's quantum mechanics. But it's not a simple quantum mechanics. It's this bonding of atoms to make molecular bonds, et cetera. This is more complicated. But the particle in a box, one electron in a box, as the box gets bigger, this is something you teach in freshman chemistry or, early physics. It's a model system. It's a toy system to begin to understand at a qualitative level and to have an actual material that shows this. That's just, to me, that's just amazing. That's beautiful. But more recently, driven by quantum optics and quantum computing applications, we've been investigating much larger particles. Instead of, the 5 to 10 nanometer range, we're going into the 20, 30 nanometer range. And it turns out, even though they don't have these visual properties, you don't see the color change anymore when you go to 15 to 20 to 30. It looks like, by eye, a piece of the bulk. But then we start doing these more sophisticated experiments, and we find that we're still not at the bulk yet. There's still these really beautiful properties that were unexpected to us that are still changing. And for the applications that we're looking for, like these quantum optics applications, quantum computing applications, it turns out that there's a sweet spot right there in the quantum mechanics evolution of the material that is really beautiful. So most of my lab now is going into that direction. At least the part of my lab that's on quantum dots.
I've heard you describe this as creating a new periodic table.
Yes. At the beginning, we were just making one material, cadmium selenide. But now, over the course of the last 30 years, people have used this methodology of not just making the particles, but using electron microscopes, X-ray diffraction, all sorts of tools to put a picture together. So use that methodology and keep true to the idea that you want a really great material system. Really focus on size distribution, crystal quality, understanding the surface. You're not studying defects, but you're really truly studying the properties that come out of just changing the size itself.
Yes.
And so now there's so many materials that people have developed within this field, not just optical materials, but magnetic materials, metallic materials, all sorts of semiconductors, and each one of them has unique properties. And if they're all well characterized and all have the same size within each material class, when you put them together, you can begin to build new constructs. You can begin to build things that look like crystals, where the particles now are the equivalent of the atoms. They form cubic crystals and face center cubic and hexagonal crystals, et cetera, depending on what you do with them. The challenge now is to get them to talk to each other. Just like atoms in a crystal talk to each other, and that generates the new properties of the crystal. You get connectivity, et cetera, et cetera. So now the challenge that people are beginning to solve is, how do we get these things to talk to each other so that the properties of the different components that you put in there, or even just the same component, when it starts talking to each other, you begin to see collective effects that need multiple atoms to talk to each other. There have been reports of people for many years now, of people making dimers. You take two particles and you connect them together with DNA or some other linker and change the difference in length between the two to try to get them to talk to each other. I would say that it's a work in progress. Slowly, we're beginning to understand what it would take to create these new properties, but there's a lot of progress.
It's obvious that the possibilities are so extraordinarily large and must be increasing exponentially as you have different materials being created, and then within each of those materials, the size of the material makes a difference to its properties. And then you can combine these, and people are producing new things all the time. The potential toolbox becomes bigger and bigger and bigger.
Yes, it can sound overwhelming.
Exactly.
I suppose if we had, an all-powerful AI, we just ask the AI, okay, so what should I use? And it would spit out the right answer. But we're far, far from that. So now it has to be the creative mind that has to try to make educated guesses on what's going to be interesting and important, and then try some things, see what happens, and use those results or the failures or the new understanding that comes to guide you into making it better. Combined with theory, I think theory has definitely a place to play in that exploration.
Absolutely. There are two strands I'd like to pick up on there. One is the theory aspect, because you came at this originally as a theorist, and indeed, I suppose your father was a theorist. You grew up in a very theoretical environment. He was a mathematician. Well, let's combine them, because there's you as the theorist, and then I wanted to ask you about your own creative mind, since you raised the idea. I don't know if you ever have a time to stop and think about how you approach problems, but do you have any reflections on your own creativity?
So from the very beginning in this particular field, theory was simple enough that you can get a lot of intuition out of it. And so it's the intuition that you gain from this fairly simple theoretical, and it may not be perfect. I think people sometimes misunderstand the role of theory. They think that you have to have theory that exactly explains the data, that matches, all the numbers that come out. But really what we're looking for is a theory that explains the trends. It doesn't have to be perfect, but if it can catch the interesting parts of the trend, where the trend begins to deviate from a linear line, for instance, or things like this, right? So it may not be at exactly the right size, but it catches this evolution. And simple theory, like if it's simple enough, then an experimentalist like me can get intuition out of that to begin to ask new questions guided by this understanding.
When you say get intuition out of it, what do you mean? How does that work?
That's actually a hard question.
Sorry.
It's something that you try to teach graduate students, how to get intuition. I guess if you have enough background and you see something happening that can be explained by fairly simple theory, then you can use your background to add on top of that simple theory, or you can try to apply that simple theory to other materials, or basically you try to extrapolate from what you think you understand to outside of the realm where that simple theory may be applicable, right? So, intuition is hard to teach and hard to explain.
I completely understand. And of course, it's quite usual to hear scientists who have done great things talk about having scientific taste or intuition or some kind of feeling for where to go. And I don't think anybody's been able to describe what that is. It's obviously the combined experience of having thought about it and done it for year after year after year. And somehow the fruition is this intuition that you're talking about. And as you say, teaching it to the young is very challenging.
I'm going to go to that teaching a little bit.
Yeah.
Because being a graduate student, and even a postdoc, is an apprenticeship. Really, that's what it is. You work with somebody who has a lot more experience, asking questions, and maybe the person like me maybe had become completely incompetent in the lab because the equipment changes so fast, and we just don't have time to stay up to date on how to work the equipment. But we've learned to ask questions, and we've learned to look at data that comes out. We know enough about the equipment that we can guide what should be done. So that 30,000-foot view of the experiment, that's what we try to teach through an apprenticeship by asking questions and having. So when a graduate student starts, they have no idea about any of this, right? So we pair them up with more senior students, or we give them a project that's to begin to cut their teeth on. And there's a lot of failure, but out of failure, sometimes there's gold nuggets, right? And so we have to teach them how to recognize these gold nuggets that they may not recognize, and teach them how to ask questions, really.
In your Nobel lecture, you referred to Louis Brus as the person who taught you how to be a scientist. I guess that many things contributed to you becoming a scientist, but was there something in particular that he showed you?
I think it's that process of asking the questions that really clicked, because it was a new field, right? So the fields that I was working on before had a massive literature behind them. Many, many groups, many communities had worked on these for so many years. They were mature fields, and the progress was evolutionary, stepwise. And, you could write a paper making a little step and making another little step, right? Which is fine, certainly fine. But the big questions of the fields were hard. They were really hard. And one person by themselves wouldn't be able to begin to address them. It's a community effort. You have to put everything together. But this particular field, when I met Louis and started to work with him, nobody else was working on this. And every question, was a new question, and guided by simple theory, because he's also, he's the one who taught me how to really use simple theory to guide yourself. Again, through this apprenticeship, right? Then when the theory doesn't work so well, you add another layer. But you don't want to add too many layers altogether, because then you lose the intuition. You lose the ability to predict what you think should happen. You abandon that and you give it to the theorist to tell you what to do. And as an experimentalist, you really need to be able to guide yourself to the next question. So he taught me that. He taught me how to think like that, which for this field has been really important.
How has it been being in a field which, as you say, when you started out in it, it was sort of yours for the taking. There was nobody else there. And now it's so huge. You've witnessed that evolution. You've been part of it. How does it feel to travel that road from having it to yourself to sharing it with so many?
Well, at the beginning, it's a little disconcerting because there are a lot of really smart people out there. And then suddenly it becomes competitive. And you realize that, I wasn't, my background was in physical chemistry, not really in synthetic chemistry. And then people with more intuition in chemistry come along and they can solve problems I had no idea how to solve before, which is great. But it makes you realize, you can't do everything anymore. You got to pick things that you're good at that really interest you. At the beginning, everything was wide open, and you could follow a path that interests you and at the same time play in other directions. But, unless I wanted to run a group of 500 people, I couldn't cover everything. So I really had to pick the directions that were particularly interesting to me and watch other people solve problems that I wish I could solve, but I can't.
But I suppose it's about having the intuition and confidence to know where to head.
Yeah.
And obviously you can't do this 24/7 for a whole lifetime, although I imagine that there have been periods where it has been completely absorbing. But what do you do other than concentrating on the work to kind of give yourself the space to reflect on what's happening in the lab, which is so necessary, I suppose, to making good decisions when you get back in the lab?
I guess I have two parts to that. There's my work life and my personal life. On my work life, as I matured as a scientist, as a professor, and became more interested in the technologies, I get interested by many, many fields and really like to learn about other things. Maybe not at a very deep level, but at least know about them. And being in a place like MIT and being exposed to engineering and other scientific fields and, medicine across the river and Harvard Medical School and a lot of startups around here, you really are exposed to so many things that are so interesting. And I love that, right? And those things give me ideas of how to go back to the lab and take different directions, whether it be applications of the quantum dots in bioimaging, which we did, 20 years ago or so, that has been really fruitful. You meet people, you meet different communities that then allow you to think about fundamental questions that you can ask in your lab, but also how to apply these things and basically touch other communities, whether that be through science or through entrepreneurship or just by learning. That feeds me intellectually. I think that's really important. If I were just working with quantum dots thinking about, or nanomaterials thinking about their properties all the time, that would be exhausting, I think. It would get old after a while. But it's the ability to then connect what you're studying to this huge scientific endeavor. I mean, I've worked with people at NASA, for instance, and from that I've learned about problems of sensing things in space, that maybe quantum dots have nothing to do with, but I love these questions that people ask, right?
And how about home life? How does that contribute to the work?
So I do take time to do things outside of the lab. I like to climb. I rock climb in the gym and outside. I have a partner that showed me the beauty of ice climbing, so I've been doing that for a number of years.
I should mention as an aside that we run these dialogues in Stockholm as part of Nobel Week, these meetings on the 9th of December. And at one of those, we had one on risk, and we invited Alex Honnold to join us.
Okay, that's a different category entirely. His idea of risk is not my idea of risk. Yeah, and I like to travel and see new places. I like to cycle. I used to be able to run. I used to run quite a bit. So I like to be outside, ski. So my lab has, since I started, I've had a retreat from my lab every year in January, February, where I rent a house for a few days, and the whole group goes up and we all ski together. And, those who don't ski, that's fine. They can learn, or they can stay in the chalet or whatever and enjoy the beautiful surroundings. And we bond together. The students all cook together for a number of meals. And this is a way for me to ski with a bunch of people.
And do you talk about work on these retreats, or is
we
it?
Always work. I mean, we talk about all sorts of things, but it's an informal way to really discuss work in a different setting where we can talk about these bigger ideas. Because when you're in the lab day in, day out, you're so focused on the details of a particular project, sometimes you lose sight of, or at least the students can lose sight of, the bigger picture. Mm. And so this is a setting where on the way up in the car, we start talking and we can just philosophize about science, where we're going, the big pictures. I think it's a wonderful way to get, beginning students to think about these things.
And when you and your partner are ice climbing,
yeah.
Does work pop into your head at those moments?
No, it doesn't. There's no room in there for anything but the surroundings and the activity that you're doing. It's a wonderful thing.
It sounds fairly perilous.
Well, I think if you can keep yourself safe, let's just say you can minimize the risk as much as you can. You look at the weather, you look at the quality of the ice, you look at all the variables, and you have to learn very quickly when to turn back.
And what's the attraction?
The attraction, it's the intense physicality, the intellectual problem solving that goes along with it. That combination, to me, that's the attraction. When you're climbing, you solve the problem. How do you get from point A to point B? Well, it's a problem. You have to solve it, right?
Is that how you grew up? Were you an outdoors sort of child, doing not perilous things, but exciting outdoors things?
Absolutely not. My father was completely removed from any of that stuff. He was a mathematician who just loved math and was actually not very good at any of that stuff. He managed to break his toe skiing, in the boots. So how does that happen?
He'd found the right path for him behind a desk with his maths, yeah.
Yeah. So when I was a child, I just loved to go out and just run or ride a bike. Mm-hmm. And I didn't really discover my taste for more active things than running and cycling until I was a professor, really, and met people who taught me showed me, this part of these activities, and I loved them.
What about your taste for science? Was that obvious to you when you were growing up? Was it clear that that's where you would end up?
I think so. I think that I was always thinking that I would go into science. Maybe there was a brief period when I thought I would go into medicine, but it was going to be science-oriented from a very early age, I think.
Do you think that's necessary for people who want to go into it, or do you think you can?
No, I don't think so. I've seen people, some colleagues, that were English majors and, were interested in science on the side and then became scientists. I don't think you need to be into science from a very early age. I think you can go into it.
These days, one of the refrains one hears constantly from young people around the world is that education systems, pressures of exams, selective education, it all makes people make decisions very young. And then it's increasingly hard to switch gear and realise that actually maybe that wasn't where you wanted to be, or that you want to switch on later.
Yeah, I think that's the feeling for sure. And I'm a really strong believer of a liberal arts education, the kind that we have in small colleges here or some universities. I think that there's certainly a trend towards a more career-oriented education that focuses too quickly on one subject, let's say, or a couple subjects. And I think it's so important to be well-read, to understand history. Science is a part of history. To understand science's role in our community, in the world, you need to understand all these other things. You need to understand social dynamics. Those things are so important. I always liked to read when I was a kid. I would get into so many books, and my parents moved around a lot, and I was constantly in new schools and new communities, and I would just get lost in novels, old French novels or translations of old Russian novels, really thick things. And I remember one year when I was 10 years old, I think my parents rented a house, and they had this collection of all the books of Émile Zola, and I started reading them one after the other. I think it's super important for us as a community, as a society, not to lose this broad education. Because when you're 20 years old, you may not know what you really want to do. And that's perfectly fine. That's really perfectly fine. And you can come to figure out what it is that interests you a little later. And you've lived a life that you can bring to that field and contribute things from a different direction. And I think that's really important.
I know you play the violin as well.
I do, yeah.
Do you play with friends?
I don't really play much anymore at all. Basically, when I got to graduate school, my violin career kind of ended. I still play it every now and then, but not to the extent that I did when I was into my mid-20s. There were too many things to do.
But it never leaves you. So.
It never leaves you, absolutely. I learned a bit of piano. I like to pick up instruments and just learn how to do simple things on them. It never leaves you. It's definitely part of you.
And if the right 3 students joined the lab, you could then form a quartet.
Yeah. No, but I love music. I love music.
It's been an enormous pleasure speaking to you.
Well, it's my pleasure.
You just heard Nobel Prize Conversations. If you'd like to learn more about Moungi Bawendi, you can go to nobelprize.org, where you'll find a wealth of information about the prizes and the people behind the discoveries. Nobel Prize Conversations is a podcast series with Adam Smith, a co-production of Filt and Nobel Prize Outreach. The producer for this episode was Karin Svensson. The editorial team also includes Andrew Hart, Olivia Lundquist, and me, Claire Brilliant. Music by Epidemic Sound. For another episode that mixes the quantum world with a touch of French literature, check out our episode with 2022 Physics Laureate Alain Aspect. You can find previous seasons and conversations on Acast or wherever you listen to podcasts. Thanks for listening.